Hello, everybody. I hope you had a nice lunch. Today, we will continue with a lecture on machine learning in natural language processing. So some of you may wonder why there is so much mathematics in this lecture. We are going to deal with machine learning algorithms and in particular with tools such as neural networks. And if you want to learn neural networks, there are books, very nice books, showing you some pictures, giving you some comments, and then giving you Python code to use them in Keras or TensorFlow, and that's all. This is one way of learning neural networks, and it's a perfect way for a Lambda user. But you are going to be engineers. And as engineers, you must be able to maybe not do research necessarily, but at least be able to learn from research. You, in your work, you will have to find out what has been done, what tools have been introduced, what methods have been introduced, and to understand them. And here I took just a paper, an arbitrary paper. It's not the most important one, it's just one paper. It has among the authors Yann LeCun, one of the most famous computer scientists who is French and Breton, and who did a lot on neural networks. The title doesn't sound very scientific. It looks like an average paper. It talks about stochastic gradient descent, something we will see today. And if you go to page 2 of this paper, you see already some formulas. For example, this formula. Today's lecture should give you the tools to understand such a formula. The symbols used will not always be the same. The terminology used will not always be the same, but once you have seen one set of symbols and one type of terminology, you will easily be able to adapt to other ones. So this is why I have used so much mathematics, because I think that there is the mathematical point of view of machine learning, and it's an important one for those who, like you, will sooner or later will have to read some research papers. So today we are going to deal with text classification, and then on the next 2 machine learning thread lectures, we will talk about language models and about distributional semantics. So 3 important subjects, and we start with the simplest one, text classification. And we will investigate 3 tools, 3 classifiers. The first one, naive Bayes, you certainly already know. We will look at it thoroughly. Then we will talk about logistic regression. And finally, about forward neural networks. So I may had talked also about support vector machines and other interesting tools, but it's not our topic. We want tools that are useful for natural language processing, and logistic regression is used a lot in neural networks. So, and naive Bayes is the symbols case. So these 3 are natural choices. And if we have time left this afternoon, we will do a lab on sentiment mining, where we will use exactly these tools. So let us start with naive Bayes. which is a linear classifier. So linear classification is whenever your set of individuals can be represented in a way such that you can separate classes using linear objects. So, for example, hyperplanes. So you can have linear separators. We will take the example of a bag of words. So what is a bag of words? If V is a vocabulary, so a vocabulary is a set of words, a vector of n in the power v. So what do we mean by that? We mean that for every item in the vocabulary, I need an integer number that can be 0, 1, or more. And this can be, for example, the number of occurrences of each word in a document. So taking a bag of words is losing a lot of information. I lose the order of words in the document, but I keep their frequencies, the number of occurrences. And let y be a variable, we don't know what, taking values in a set of classes, y. We want to predict y, and we will write our prediction as hat y for a given x using a linear classification. Now, for this to be in a general frame, we define a feature function. Now, what is a feature function? It is essentially a vector, theta, and a function which I call f. I don't know why it should be called f, but this is how it's written. And this is not just any function f, it's a very specific function where you have a lot of zeros, an x, so the vector x, and again zeros. So f is identity in part of the vector and 0 in the rest. So which part of the vector is identity? It's the part that takes the value of y. So f depending on y will be a vector where for the value of y we will have x, and for all other values we will have zeros. That's all. And this allows us to have a theta as a very long vector with different copies of theta for each value of y. And the scalar product will be such that depending on y, for each x, we will have the appropriate theta. So it's a trick to simplify notation. And now, what will be our prediction? The prediction will be the class I predict for x will be argmax of this feature function. So my feature function will be such that by taking the maximum value for all possible y's, I get a prediction for x. Our first case of classifier in which we will use this psi is naive Bayes. So in naive Bayes, psi is the joint probability of x and y. But be careful, we have parameters. So here P is not a probability, it's a probabilistic model. It's a function we will define, since we are doing parametric models. It's a function we will define and which will depend on the parameters mu and phi. And once we have defined this model, we will get our prediction by taking argmax of this for all y's. So which is the class y for which this function, which we will define, gives us the highest value. Now, the highest value of this function is also the highest value of that function because log is an increasing function. Now, mu and phi are the two components of theta, and theta is what I've used here in this notation. And this parametric probabilistic model is defined as follows. First of all, naive Bayes is called naive because it presupposes, it puts some very strong hypothesis on our system. For example, it says that all x's are independent conditionally to y. And therefore, the joint probability is the product of individual probabilities, always conditional to y. This is a very strong hypothesis, which is wrong in many cases, but it allows us to do some very nice calculations. So this is the hypothesis of naive Bayes. And thanks to this hypothesis, I can have a formula where this probabilistic model is the product of two well-known probabilistic model, which is the categorical model for y multiplied by a multinomial model for x. And I will give you the exact formula in a moment. So this means that we know exactly how we model the situation. All we need is values for mu and phi. So how do we calculate mu and phi? Once we have chosen a probabilistic model, how can we obtain the best possible values of mu and phi so that our model is the closest possible to the real case and our predictions are the best possible? For this, we will use something called maximum likelihood estimation. So maximum, what is likelihood? Likelihood is, again, the joint probability, but this time considered as a function of the parameters, mu and phi. And the maximum will be the maximum for depending on mu and phi. So we will maximize the probability on the training corpus and obtain the values of mu and phi that give us the highest probability for the corpus. Okay, so here we have a very interesting idea. It's saying that we consider our corpus as being the truth. This truth may be probabilistic, it may not be absolutely consistent. The same features may in one case belong to one class. So an individual with the same features may belong to one class, and in some other case in another class. So it's not strict, it's not deterministic. But if we manage to find values of mu and phi that give the highest probability for the whole training corpus, then we can use these values for predictions. So whatever knowledge we get from the training corpus, and this knowledge are the values of mu and phi, we can use to make predictions. This L, like likelihood, is now the calculation of this likelihood estimation. So likelihood, as I said, is taking the same formula as here, and considering it as a function of mu and phi. The T here means that it's on the whole corpus. And by the naive Bayes hypothesis, this joint probability is the product of the individual probabilities. And here, parenthesis I means the ith document. So here, the product is over the documents of the corpus. So the probability of the whole corpus is the product of the probabilities of each document. And for this one, I have the formula. Here is the model I have chosen in naive Bayes, product of categorical multinomial. And for the multinomial, I have a formula which is as follows. We first have a term with a capital beta, which is a multiplicative factor. And that depends only on the value of x for each word, so the frequency of each word. And here I have my parameter phi. So what phi is that? This is the phi of document yi, component j, and I'm taking this parameter with a power, the power of xji. So this, again, is a value. In fact, it's the frequency of the word. So I'm multiplying it. I'm taking the power of the frequency. So intuitively, if I know that I have a word which has a probability, and I know that all word occurrences are independent, this is an hypothesis, then having the word twice will have the probability of having the word times the same, so times again the probability of having a word, so it's the square of the probability of having the single word, and so on. So having the word n times is the probability of having it once at the power n. So don't get confused by the many indices here. This is I is the document. This is why I put it in parentheses. And J is the component. And when we say component, we mean the elements of our vocabulary, of our bag of words, the coordinates of our bag of words. The log of a product is the sum of the logs. So here I have the log of the product of the categorical probabilities. So this product becomes a sum. Here I have the sum of all the bxi's, and these are just multiplicative factors. And here I have the first product becomes a sum, second product becomes a sum, and here I have log of phi power x, so it's x times log of phi. And this is the result. This is a way of representing my likelihood. Now, this formula is interesting, but what I want is to maximize likelihood with respect either to mu or to phi, or both. So let us maximize it with respect to phi. If I look at the formula, this part doesn't depend on phi at all, and this one neither. So this is the only part that depends on phi, on some phi. So I keep only this part. And this part is a sum on I, so I are the documents. And now I want to maximize, so essentially take the derivative of this with respect to phi y. So what is this y? Y is a value of the class. So this is something I want to predict. And here I have documents. And each document has some value of the class. So I'm training, so I know the classes of my documents. And I'm interested not in the phi of a given document, so a phi of the class of some document, but phi of some class y. What I can say is that this sum can be split into two parts. The first part is the case where the document has the same class y, belongs to this class. And the second part is the remaining whenever the document y, and not y, the document I does not belong to that class. So this is a very simple splitting into two. And this splitting allows me to write here a y at this location. I'm not sorry, it's hard to mark it. So at this location where I'm pointing at, I can write a y because all of these documents belong to class y. Now, if I'm looking for those depending on phi y, then it's only the first part of my sum. And I also have a constraint that the components of phi for a given y must have a sum equal to 1. So this is part of the model. Okay? Now, I have this left part of the sum and this constraint. How can I combine this part and the constraint? Well, there is a method called Lagrange Multipliers where we write the constraint as something equal to 0. In our case, it will be sigma j phi yj minus 1 equals to 0. And we take the formula, minus lambda, where lambda is scalar, times the constraint, the part which is equal to 0. We get a new formula. This new formula is a function of lambda, but also a function of phi y, and we maximize it. And this maximization will give us a solution of the formula plus the constraint. To maximize it, we take the derivative. The derivative with respect to phi y. So phi y is a vector. So in fact, I will write nabla. And this nabla will have many coordinates. Each coordinate will be the derivative with respect with yj. Okay, so imagine this as being a vector with these components for every j. Here I have the formula. What happens if I take the derivative? I have this part, well, where this is a multiplicative factor. Then I have the log of what I want to derive. So what is the derivative of the log? So it's 1 divided by this, multiplied by the derivative of this, but this is exactly phi y, so it's 1. And this part derived with respect to phi y gives me exactly this. You see, you have phi yj in the denominator and the multiplicative factor xi here. And the rest, where here you have just a lambda factor. Among this sum, we are only interested in phi yj, so we keep only 1. And the derivative is 1. And then this is a constant, so derivative is 0. So here is our derivative. And this is what we want to set equal to 0 to get an extremum. And setting this equal to 0 gives us phi yj equal, setting this 0 is this sum equals to lambda. And then I can raise phi yj and get lambda phi yj equals to sum xj. And this lambda is not important. What I retain is the fact that they are proportional. So in fact, phi yj is proportional to this thing. Now, what is this thing? Xj is the number of occurrences of a word, and xji is the number of occurrences of word j in document I. Now, the sum is over all the I such that the class of the document is y. So in fact, what I'm counting is the number of occurrences of word j in all documents of class y. So it's the count of j in class y. At least it's proportional to this thing. Now, proportionality is not enough, but we do have another information, which I used already here, information saying that the sum of all the phi yj is equal to 1. So this is part of our model. This means that to get the exact value of phi yj, I just need to divide by the sum of all the phi yj for all j's. So this means that finally, what is phi yj is how many, for each j, it's how many times j appears in class y divided by the count of all words of class y. So divided by the size of class y. So in fact, it's the relative frequency estimator of the word j in the class y. So you see, instead of saying immediately that naive Bayes for the example of a bag of words will be based on the relative frequency estimator using this formula here, I started with the probabilistic model. I examined when it's optimal. So how do I calculate mu and phi by using the likelihood? When is the likelihood maximal in these cases? And I arrived at the conclusion that in this case, phi yj is the relative frequency estimator. And I can do the same thing with respect to mu. So once again, in my formula for the maximal likelihood, which is here, I keep only the part depending on mu, this part, the rest has no mu. I keep this part. Again, same trick. I can write this as one part in which I can replace yi by y. So I take all documents. That's probably not a question. So let me mute it out. Okay. So again, I'm splitting the sum into two parts. And this allows me to keep here mu y for a given class. Okay. So you see the trick is to say this depends on a given document. What I'm interested in is mu for a given class. How can I obtain the class out of this? Well, I take the documents that are in that class and then the documents that are not in the class. And when deriving, this part will disappear and I will keep only this part. Okay. And again, we have this constraint, which is part of the categorical model. What is the categorical model? Is simply the probability of each class. And since they are probabilities, but the sum of all probabilities is equal to 1 by definition. So this is part of my model. Again, I can use Lagrange multipliers. Here it will be sigma mu minus 1 equals to 0. And here I have this part. So the Lagrange multiplier will be this part minus lambda, this constraint. Again, I can derive this. The derivative will be 1 divided by mu, since it's a log, minus lambda, since here I have lambda mu y, which means that the solution, the extremum is obtained when I have this equals to 0. So this sum equals to lambda, which means that mu y is proportional to units, the numerator. How many units? Well, 1 unit for each I in the class y. So in fact, this counts the documents in class y. And as I know that the sum of all mu is equal to 1, I get not just proportionality, but exact identity. Mu y is the number of documents in class y divided by the number of documents, the global number of documents. And it's again a relative frequency estimator, this time frequency of documents for a given class. And I wrote these slides in a way that you can recognize the same tricks, the same approach in both cases, for phi and for mu. And this means that in this model, I first have the frequency of each class of documents multiplied by the relative frequency of words in the class, in documents of the class. Now, this all looks very nice. This formula is very elegant, but there is a problem. What happens when a word does not appear in a class? It means that the probability of having this word in the class is 0, since it's the relative frequency. But this is only one term of this big product we have here. And one product is 0, the whole, one term is 0, the whole product is 0, so the whole probability is 0. So this means that one word is missing and the whole probability gets 0, which is not a good thing. To avoid this, we use what we call smoothing, Laplace smoothing. And smoothing will simply add a term, always the same, at least in Laplace smoothing. And when we add this term to the numerator, we have to add it also to each term in the denominator. And so we get here the size of the vocabulary times the same alpha, so that we keep the property that the sum of all the phi is equal to 1. So these are probabilities, but they are smoother in the sense that they are never 0. And depending on the value of alpha, they can be quite close to each other or not. So if I take a big alpha, if alpha is big relatively to this count, then this count is not important anymore. And I will get always more or less the same values because only the alpha counts. Now, how can we interpret smoothing? First of all, this is part of the bias variance trade-off. So a small reminder, what is bias, what is variance? Variance is the dependency of your model with respect to small changes of parameters. And when parameters are calculated from individuals in a training process, high variance means that choosing different individuals, slightly different individuals, can change your model a lot. And here it's a typical example. Without smoothing, if in my individuals, so in my set of documents, I happen to have a document with a word not appearing in a class, then immediately this probability is 0. So it's not small, it's 0. This means that appearance or not appearance of this word will change a lot the model. And this means that we have high variance. This is not the case anymore with smoothing, so smoothing reduces variance. But smoothing introduces bias. What is bias? Bias is the systematic error we get, and which is not depending on our training individuals, but depends on our method. So here in the method, we introduce this term out of nowhere. So we do change the values of our features, the properties of the individuals we are using for training, and we change them in a systematic way. And this is typically bias. So now we have less variance, but more bias. And it is a common problem that when you increase one of the two, when you decrease one of the two, you increase the other. So machine learning is often a compromise between bias and variance. Now, this method of smoothing can avoid overfitting. What is overfitting? Overfitting is when your model is so close to your training individuals that it has bad performances on new predictions. To avoid overfitting, you need to generalize your model. You need your model to be more general, not depend entirely on your training set, and being able to do predictions outside the training set. And smoothing does this. Why? Because it has less variance. Having less variance means having less overfitting, because your prediction depends less on your training set and more on the general characteristics of your model. But again, if you smooth too much, then you will get underfitting, in the sense that if alpha is big with respect to this count, then the count doesn't count anymore, doesn't prevail, and you will have the tendency of giving always the same predictions, and this is underfitting. So not using your training set sufficiently well. Here is the code in the scikit-learn package for multinomial naive Bayes. It has some parameters, and now you can understand these parameters completely. First parameter, alpha, is exactly the alpha we used here. So it's the parameter used for smoothing. By default, it's equal to 1. So you see that when you use the multinomial NB class of the scikit-learn package, you have already, by default, smoothing equal to 1. And 1, you see, is minimal in some sense. Well, we could choose a smaller value, but here we have counts. So these are integers, and we're just adding one value. So it's natural with respect to these counts. Another parameter is fit prior, whether to learn class prior probabilities or not. So what is a prior? If you remember from the Bayes theorem, you have a posterior equal to likelihood times, oh, I'm hearing echo. Okay. You have posterior equals to likelihood times prior divided by evidence. So the Bayes theorem says that I have a prior knowledge of something, and I get new evidence. I can calculate the likelihood of this evidence, and by taking the product, I'm getting posterior, so I'm getting new knowledge on my phenomenon. And this is how science works. We have belief, we have an understanding of some phenomenon, we do experimentation that gives us likelihood and evidence, and by combining this, we get new understanding, new belief of the phenomenon, which is the posterior. So in our case, prior is simply this part, the probability of classes. And the idea here is to say, you're giving me a training set, okay? This training set uses classes, okay? Do you already have knowledge on these classes? Or is this training set all you know about them? If this training set is all you know about the classes, then I will calculate the frequency of each class, and this will be my prior probability. If I have better knowledge, which is extrinsic, which is not based on my training set, then I can give this using the class prior parameter. And then I say, okay, no matter what you find in the training set, here are the frequencies of classes. And if these classes have uniform distribution, then I just need to say fit prior equals to false. Then this package, this class, will consider that all classes are uniformly distributed. Okay. And here is a complete example. I'm even using a small corpus, which I will show you. It's on Moodle. And I have, on Moodle, I also have the URL where you can find this data set. You see, these are sentences. They are opinions of users about, I guess, restaurants. They mention potatoes and burritos and waitresses. So it's about restaurants. And every sentence is followed by a class 0 or 1. So I have a binary classification of good and bad critics. And you see here, service was very prompt, good critic. Will not go back, bad critic, and so on. And this is a really horrible corpus because sentences are short. Sometimes they are not complete sentences. The burritos, blah. So there is no verb. The food, comma, amazing, no verb. Sometimes you have negations, not worth. So it's a bad corpus to process in a rigorous way. So a syntactic analysis of this corpus will give me rather bad results. And there are techniques for normalizing, and Tian has worked on that in her thesis. But here we will do the simples. We'll take the simplest possible approach and just apply naive Bayes. So let me return to my slides. Here we are. And as you see, we use pandas. We use a count vectorizer this count vectorizer will take a data frame. So here is my file. I'm reading this file as a comma-separated values file. Instead of commas, I have tabulations, and I store it in a data frame with the column sentence and label. I take all the sentence values and put them in an array. I take all the label values, put them in an array. I instantiate a count vectorizer object, and this one will take the sentences and vectorize them. So it creates the back of words. It takes words and creates the vocabulary. The vocabulary is gives a vector, and for each sentence, this vector will contain the frequencies of words in the sentence. And of course, here there are many options which we don't have time to explore, but there are many ways to do this by omitting stop words, by ignoring lowercase, uppercase, and so on. So here I have my back of words for all sentences. And here I instantiate a multinomial naive Bayes classifier. And then I have this very nice Python function, which is cross-validation. So what is cross-validation? Instead of defining a training set and a testing set once, I divide my complete set into how many? Here, 20, in this case, 20 parts. And I do the same set of predictions 20 times, each time using a different testing set among the 20 parts, 20 equal parts. This is called cross-validation, and it's very useful because every individual in my set becomes part of the testing set, at least, not at least, every individual becomes part of a testing set exactly once. And every individual is part of the training set exactly n-1 times, here 19 times. By writing this and giving the classifier object, Python will do this cross-validation 20 times and return the scores obtained. So this is an array of 20 values, 20 scores, and I can ask for the mean, which is the most interesting, and also standard deviation. And here I get an accuracy of 0.8. What is accuracy? It's the number of correct predictions divided by the number of predictions. Accuracy is the simplest way of measuring the quality of some classification. Better than accuracy, you have precision and recall, but precision and recall are class dependent. So you will have a value of precision and a value of recall for each class. Accuracy is global. And this ends the part on naive Bayes. Our next classifier is logistic regression. So there is already one big difference between logistic regression and naive Bayes. It is the fact that naive Bayes is what we call a generative model, in the sense that what we are dealing with is the joint probability. So it's not only the probability of having a class for a given for giving individuals, or the probability of an individual of being in a given class, conditional probability. It's the joint probability of having the individuals and the class together. This is called a generative model, while the logistic regression is a discriminative model. So discriminative models are studying the conditional probability of having the class given specific individuals. Again, we will use a parametric model with a parameter theta. So this is the first specificity of logistic regression, is that we will calculate conditional probabilities. And the second one is that it is linear classification, since we have, again, this scalar product. But this time, we take exponentials. So we take the exponential of the scalar product, and to be sure that our model is a probability, we divide by the sum of all exponentials, so that the sum of all of these terms is equal to 1. Okay, so once again, we define a probabilistic model, which is this formula. And our goal now is to calculate theta in order to optimize a model, in order to have the best possible performance in prediction. What will be prediction? Exactly the same as with naive Bayes. It's the argmax of what? Of this model. So which class gives the highest probability for a given individual? Again, to calculate theta, we use likelihood. Only this time it's called conditional likelihood, since it's conditional probability. And once again, we have a log, and we will calculate the theta over the training corpus. So you see this slide looks a lot like this slide. I'm using the same methods as for naive Bayes. I'm taking likelihood, which is probability, but as a function of my parameter, theta. Here is the formula. Once again, I have the hypothesis on the independence of documents. So this conditional probability is the product of probabilities for each document. So this means that documents are independent. The log of the product is the sum of the logs. And this one, according to my formula, is the log of a fraction. So it's the log of the numerator. The log of the numerator is the log of the exponential. So log eliminates the exponential, and I get only the scalar product. And here, since it's a sum, I have to keep the log of the sum of the exponentials. So this is the log of the denominator. And this is typical in these kinds of machine learning algorithms. You often have logs of sums of exponentials. It's called the log sum exp. Likelihood is considered as a function of the parameter. So we want to maximize this with respect to theta. We will take this part, which is the summand for a given I. and we will call the negative of is the loss. What is loss? Loss is a function that allows us to evaluate our predictions. So loss is something that becomes zero when our predictions are good and increases when our predictions are bad. Likelihood is the opposite. Likelihood is high when our model is good. So this is why we take the minus here, to invert this tendency. Okay? Now, once again, we have a problem with the calculation of theta. Imagine a very special case where you have a given feature J. So these are bag of words, so J will be one word. And imagine that this specific word J appears only in one document. This means that if I take a very high theta for this document in this class, and very low thetas, negative thetas, for this word in other classes, then I can get an arbitrarily high likelihood and an arbitrarily low loss. Why? Well, I'm cheating. I'm forgetting all other features. I'm concentrating on that feature. I know that it appears only in one document in a specific class. I increase the theta for this word and this class, and this, yes, in this class. I decrease all the other ones, and I'm getting a very good result. Okay, but that's cheating, and this will give me a very, very, very bad model. Because if in that, if I want to do a prediction and this word is not there, then my model, my prediction will go bananas. Okay, how can we avoid this? Well, how do I cheat? I cheat by putting higher thetas in one case and negative big thetas in the other case. So to prevent this, to avoid cheating, I'm adding to my likelihood or to my loss function the norm of theta. Taking the norm will be big depending on the absolute value of theta. And if theta is a vector, it will be the module of this vector. And if it's a matrix, it will be the sum of squares of all cells in the matrix. And this will strongly prevent having big values of theta. So it's like smoothing. It's a method for introducing some bias, since our loss is not anymore based only on getting predictions close to real values. Now our likelihood is based also on this other factor. So we are introducing bias, but we are improving performance of our model because we avoid this kind of phenomenon. And this is called regularization. This norm can be quadratic or linear. So this typically will be the max, and this will be Euclidean typically. And there is also a combination of the two called elastic net, where you have an averaged sum of quadratic and linear. Okay. And now we still have the problem of minimizing loss or maximizing likelihood. Same thing. Again, I will take the derivative with respect to theta. And this derivative, it's simply the derivative of this. Here, I just have a product. So I collect this term, which doesn't contain theta. And here, it's the derivative of the log of a sum of exponentials containing theta. So the derivative of the log will give me a denominator, and then the derivative of the sum is the sum of the derivatives. The derivative of the exponential is the same, multiplied by the derivative of the part which is inside the exponential. And this derivative, again, I have a product, so only f remains. You see, this is simple derivation, high school derivation. And here I recognize my probabilistic model. So this part, without the f that is there, is my probabilistic model. And taking a probability of something multiplied by a function of this something for the same x is what we call an expectation. And here I have a conditional expectation because it's a conditional probability. It's the conditional expectation of the function f. So is this an intuitive result? Yes. Here I have the values of my training set. And here I have the expectation of value based on the training set. If I can get the expectation close to the real values, then it means that I have a high likelihood and a low loss. So it's quite intuitive. And of course, to this thing, we add the part that comes from regularization. And so we get also here a lambda theta if our regularization is quadratic. How do we calculate theta in this case? Here you have no theta, but here there is a theta hidden in the calculation of the expectation, because this expectation is with respect to parameter theta. Okay. Okay, so how do we calculate the best possible theta? We use gradient descent. What is gradient descent? It's an iterative process. Oops, here, sorry, this should be a real theta. It's a backslash missing in the text code. In this iterative process, I'm starting with some value of theta that can be arbitrary, and I'm doing steps replacing this value of theta at step t by the same minus something multiplied by this gradient. Now, when I multiply, when I replace theta by this thing, it means I'm getting closer to having the maximum of likelihood. Because each time my gradient becomes smaller, since the new gradient I calculate has this factor that makes it smaller, and I repeat this until my result is good enough. And by this, I obtain, after some iterations, an optimal theta, a theta that gives me a gradient which may not be zero, but is close enough to zero for my purposes. Now, what is this factor? And remember, you have seen this in the paper by Lequin here, eta 0, eta I. This is the learning rate. The learning rate means how much do I optimize theta at every step of my process. If the learning rate is too high, then I may go too far. If learning rate is too low, then it will take me many steps to get where I want. So learning rate is a parameter you can play with. It's called a hyperparameter. If your gradient, if your likelihood is convex, this means that you have a global maximum or minimum. So maximum for likelihood, minimum for loss. If you have a global extremum, then you will get there sooner or later, sooner if your learning rate is high, later if your learning rate is low. If your likelihood is not convex, it means that you can have many extrema, local extrema, and probably one global extremum. Depending on the learning rate you choose, you may miss some local extrema and land in some other local extrema. So playing with the learning rate can be just a performance parameter when your likelihood is convex, or can be something more serious if it is not convex and you have to find, and you want a global extremum. And in that case, we have other methods for finding global extrema. Now, what is optimization? Optimization is how do I proceed to find the an optimal theta. I can recalculate the gradient at each step. This makes a lot of calculations. I can recalculate the gradient for each instance, for a given instance. So a given document chosen randomly. Or I can take a set of instances, a set of documents, and calculate on those. So this is batch optimization. I calculate the gradient for everybody. If my training set is not very large, I can do that. I can choose a given element in the training set and use it to calculate the gradient. Of course, this introduces variance because depending on the choice, I may get something different, okay? But it's much faster. And it's called stochastic gradient descent. Stochastic because I'm choosing randomly the document on which I base the next step. And mini batch is some kind of compromise between the two, since I'm taking not just one document, but many documents and calculating on them. It's a compromise because I can take a number of documents which is big enough to decrease variance, but big enough to be significant. And of course, the learning rate eta can change with respect to t. So I'm not, this is why I put here the parameter t, which is the number of steps. And at every step, I can change also my learning rate. So here is the code. Once I'm finished with logistic regression, we will take a break. So here is, once again, the scikit-learn class for logistic regression. And here, now you can understand the different parameters. What is called penalty is, in fact, what we called regularization. So it's a penalty on the size of the parameter theta that we calculate. What is called solver is the optimization method. So this is an algorithm, since we have many steps. And this algorithm solves our problem. So this is called a solver. And these different values are different ways to change the learning rate according to your parameters. Max eta will be the number of iterations, a maximum number of iterations, so that our model doesn't take infinite amount of time. L1 ratio is when your regularization method is elastic net. You need to weight the combination of linear and quadratic norms of theta, and L1 is the part of the linear norm. So when putting L1 ration, if you ask for elastic net with L1 ration equals to 0, it's like asking L2. And by none, you don't do any regularization. Here is the code for the same corpus, and we get a slightly better accuracy. What it's really very low, from 800 we get to 810, 11, and standard deviation is more or less the same. Okay, so it's time to take a break. Many of these things you knew already, but I wanted to introduce notation, be clear about concepts, and I wanted you to get used to these formulas, since we are going to use them with neural networks. So let's take a break. It's 14:53. Let us start again at 15:10. Let us return to lecture. Before moving to forward neural networks, let us review what is important to keep in mind about logistic regression. We have a specific probabilistic model. So this may sound trivial to you, but I do like to repeat it. It's that a probabilistic model is not a probability. A probabilistic model is just a function we define that has the properties of a probability, so it's additive, the sum is equal to 1 and so on, positive between 0 and 1, etc. And it has a parameter, one or more parameters, and we rely on this probabilistic model to give us values close enough to a probabilistic distribution, and we use it to make predictions. So in the case of logistic regression, the model we have chosen is this one, exponential of a product between a parameter theta, which is a vector, and this function, which is equals to x for a given y and 0 otherwise, divided by this term in order to have the properties of probability. So this is the one thing to keep in mind with logistic regression. And the other thing is that we calculate theta to maximize likelihood or to minimize loss using methods of gradient descent, which can be either deterministic or stochastic. And gradient descent means taking steps and getting closer to the optimal value for theta at each step with a given learning rate. Now, imagine the following situation. Again, you want a classification, and again, X is a bag of words. So you have X, which are your classes, for example, good, not good, or if it's a forum, then culture, sports, news, etc. And your words X have some features, which we will call Z. For example, a feature can be, it's a positive adjective. So an adjective with a positive sentiment attached to it. Or it's a noun with a positive tag. Or it's a verb with a negative tag, the verb to hate. Or something else. So we can imagine those features, and we can say, we can train logistic regression on these features, conditional to words, and then we can have a separate classifier, again, logistic regression, to obtain classes of documents with respect to the features. This means that we have 2 layers. Well, in fact, we have 3 layers, and out of these 3 layers, we get 2 logistic regression classifiers. Okay? And now there's a trick. The trick is that maybe we don't know these features Z after all. Maybe we just guess there might be features like that. We don't know them, but we consider that it would be nice to consider them in some way. So we don't have the real values of Z. We don't know whether a word is positive or negative, and if this is a feature or not. What do we have? We have the probabilities. And these probabilities are calculated by logistic regression. So here we take advantage of the fact that logistic regression is more than just a classifier in the sense that it will say yes or no. Logistic regression gives us a value, for each z and each x of conditional probability, of what we consider as being close to the conditional probability, and we will get closer and closer by calculating our parameters. So instead of using values for z, we will take the probabilities calculated by our classifier. And having this architecture and this trick, we get a feed-forward neural network. This network, it's a very simple one. It has only 3 layers: an input layer, output layer, intermediate layer. I call X the input layer and Y the output layer to keep the same notation as I had here for the logistic regression and naive Bayes. So even though it's not logical, I take Z as the intermediate level. And mathematically, this neural network will be a first logistic regression, which to keep things simple, I will consider as binary between the intermediate level and the input level. And it's logistic in the sense that my model, my probabilistic model for this situation is based on the logistic function, which is 1 divided by 1 plus exponential. So sigma is used universally for this function, which is called logistic function. It has the nice properties of going from 0 to 1. So when x goes from minus infinite to plus infinite, the logistic function goes from 0 to 1 in a very smooth way. It looks like an S. And here, don't be afraid by this notation. This notation is there only to frighten you, or maybe not you, but those reading the text and not knowing what it means. It simply means it's the layer going from X to Z. Okay. K will be my individual. So this is 1, 2, 3, 4, K. So this is called a neuron. So this will be the kth neuron, equals to 1. It takes the value 1, and my model, which is a conditional probability model, says depending on X with parameters capital theta. Why do I use a capital theta? Because it's a vector, and it has components. And in fact, it's more than a vector, it's a matrix. Why? Because every component, K, corresponds to some individual. But the individual, X, can be a vector also. So we have columns, theta K, which have components, and I take a scalar product with X. So depending on the nature of X, this can be a vector or a scalar, and capital theta can be a vector or a matrix. So playing with dimensions like that brings us to a new concept, the concept of tensor. A tensor is simply a generalization of a matrix. A matrix is 2 dimensions of cells. A tensor can be 3, 4, 5, as many dimensions as you want. Okay. And there's one additional detail it's that X, and this should be bold X, sorry. It contains a component. So one of these things is one of these things, sorry, is an artificial one equals to 1. Why do we do this? Because by putting a 1 here and having an additional term, we can control bias. These terms are independent of the training values, and they are learned separately. So at the first level, I can consider that this value is just 1. This value participates in the calculation of this layer of thetas. And at the next layer, I will put a B like bias. And this B is obtained out of calculations from the previous layer, and it allows me to rectify the bias of my results. Okay, so this is common practice in neural networks to have all of your neurons obtained from data plus an additional one to obtain the bias, an additional one on each level. This is the first level. It goes from X input to Z intermediate, and this is the next level, from Z to Y. And the model is again a conditional model. Y equals to something, and here I can have more than 2 classes. And the probabilistic model is that for value J of my class, I have the jth component of a vector. Each component of this vector is a softmax. So what is softmax? It's just a nice word for saying the exponential of the jth component divided by the sum of the exponentials of all components. So what is softmax? It's a transformation of a vector into a vector. The input vector can be a vector of arbitrary real numbers. The output vector will be between 0 and 1 and will have the properties of a probability distribution. So why is it called softmax? The max part is not very clear. The soft part is because using exponentials, I get something infinitely differentiable. Now, you have learned neural networks probably by examining the process from a data driven point of view. So you have probably learned neural networks by saying, in my input layer, data is entering, and it is sent to the next layer multiplied by coefficients. When arriving at this layer, the layer does first the sum of all entering values, and then goes through an activation function. And then it sends the value to the next layer. So this is a dynamic point of view. Who is sending what to whom, and how does information, how do these numeric values transformed to get to the next layer. Let's see if we can recognize this in here. These are the coefficients. These are the input values. This is a scalar product, so it's the sum of pairwise products of components. So it's exactly the same thing. Take individual values, consider them as components of a vector, and multiply by coefficients also considered as components of a vector, and take the sum. So this is the first step. And then activation function, here I've chosen sigma, and here I've chosen softmax. So sigma and softmax are just what we call activation functions. In the dynamic point of view, if we think of real neurons in our brain with electricity, blah, blah, blah. In our case, since we are dealing with classifiers, sigma and softmax are our probabilistic models. These are the formulas we choose to use to get model as close as possible to a real world situation. The trick I mentioned is, instead of taking this conditional probability as a probabilistic model, to say that Z is what we got from the first layer. So we don't calculate the probability of Z being something because we don't know what Z is. We take Z as being exactly this thing. So it's not probabilistic anymore. It's just the activation of the sum of the products. And we can put this into the formula of the next layer. And so the last layer, the output layer, conditional to the first layer, using all the parameters of the neural network. So parameters of the first layer, parameters of the second layer, parameters of the first layer, and bias becomes the softmax of this thing multiplied by Z being that thing. So it's the first one times sigma, the second one times sigma, the first one plus B. And this is now the probabilistic model of the complete neural network. And now all we need to do, as we say in French, yaka, all we need to do is to calculate the parameters, the thetas, the many thetas, and the B's. We used twice logistic regression, so naturally, again, we will use maximal conditional likelihood on a corpus with n individuals, with n instances. Here it is. So this is our maximum conditional likelihood. Now, let us do a trick. The trick is to say, I take this model of mine for each j, and I give it a name. Now, what is this? It's something I have calculated from the corpus. So it's a prediction. The prediction for, not for a new individual, but for an individual of the corpus of being of class J. Okay. So it's like saying, of course, I know what is the class of this individual. It's part of my training corpus. So I use this to train my model. I trained the model. Now I have a trained model. When I question this model, what is the probability of individual I being of class J? If the model is well trained, then I should get a high value, or at least a value higher than all others. But I won't get a 1 because my model is not sure about individual I being of class J. I will get some value between 0 and 1, hopefully high. So this is the prediction for an element of the corpus. I call it Y tilde for class J and individual I. So this log here on the first line is the log of Y tilde. Only this one is for a given J, and this is general. Okay. Now, let us define as E a vector that has as dimension the number of classes with a 1 at position given as an index and zeros otherwise. So it's like an indicator function for this dimension, like a Dirac function, if you want. Okay. If I take all J's, then I get a vector, which I write with bold, because it's a vector. I don't write the J because it's a component. And I'm interested in the component for which I have the real class of individual I. That component is the component yi. Okay? Which means that if I multiply this vector by this vector, I get exactly this. Okay, it's a trick. Instead of taking just this expression, I produce a vector out of this, and this vector has one value for every j, and I multiply this vector by another vector, which is very simple. It has only one at single position, but not just any position, the position which is the real value of class I, of individual I. If I take the scalar product of these two vectors, I get this thing. So I have rewritten my conditional likelihood as a scalar vector of two things. This is very, very artificial, but it gives us an insight. The insight is that we can consider this expression as a crossed entropy. So remember, what is entropy? It's the information hidden in something. And what is crossed entropy? It's a way of comparing two probability distributions. It's not symmetric. It's not zero when you take the same probability distribution. When you take the same, you just get simple entropy. But it's still a way of comparing them. And here's the formula when your probability distributions are discrete, which is our case. So the crossed entropy of P and Q, probability distributions, is the sum of P of x log Q of x for all x's, which means that if your probability distributions are different, then you will have a high crossed entropy. And if they are close to each other, you will have a low crossed entropy. Now, this is a crossed entropy, and the probability distributions I have is this EYE and tilde E, tilde YE. What are these? These are the real values of the individuals, this vector. We can consider that it's probability 0 for the false values and probability 1 for the real value of the class of a given individual. So it's some kind of probability distribution that gives me the real value with no uncertainty at all. And this, as we defined it, is the prediction of having the real value. So it's how much my model allows me to predict that a given individual has the correct class value. And this means that my loss is comparing real values with predictions. And this is perfectly intuitive. How good is my model? My model is good if real values are close to predictions. My predictions are close to be true. And I'm not doing this on new individuals. I'm doing it on the individuals of my corpus, on my training set. How will I calculate theta? Using this as a loss function. See, I have a negative here, so it's negative likelihood, it's loss. This describes entirely the neural network. We have a first layer, sigma, so logistic function, upon coefficients times input values. One of these input values being 1 to have a bias. Then the prediction is the model applied to second layer coefficients times what we obtained here. And here I need bold Z, sorry, error, plus the bias. These are the calculations of values, and this is the loss. The loss is this vector with the real value of individual I times the log of the prediction. And these three steps will allow me to define my stochastic gradient descent. So what do I need to define? I need to calculate thetas and b's. I have two kinds of thetas, thetas for the first layer and thetas for the second layer. B's will be modified at each step by the learning rate multiplied by the gradient of the error with respect to B, and each one of the thetas will be modified again by learning rate multiplied by the gradient with respect to this theta of the loss. So you see, this is quite easy to understand. I take parameters I need to calculate, and I progressively get them closer to optimal values by multiplying always by learning rate times gradient, only the gradient is always with respect to the given parameter. My first calculation will be the one of the second layer. So theta of z to y. This is my model, so I just need to put here the formula for my model. And it's taking the gradient of this with respect to the thetas. So I get the formula. The loss is here, and this was this. Okay, so I'm leaving this as it is, minus 1. So this 1 comes from, where did it come from? From the, from here, from the Softmax. ZK. And what is ZK? The value of the corresponding neuron on the second layer, the first on the Z layer. So I'm first doing this calculation, and then with the values obtained, I do the calculation of the first layer. And here I apply the chain rule. So I introduce the Z's, and I know the relation between the Z's and the X's, and I get this. So this is something you saw already. It's called back propagation. And when we do our calculations, we go from the input layer to the output layer. And to optimize the values of parameters, we go in the other direction. So we compare the output layer with the results we want to obtain and go back to the first layer, calculating and reusing our results. Like we did already in the case of logistic regression, again, we need regularization to avoid thetas becoming too big. And therefore, we define this loss that adds components for both kinds of thetas, thetas of the second level layer, thetas of the first layer. These are matrices. What is the square norm of a matrix? It's called Frobenius Norm, and it's the sum of the square of all cells of the matrix. So we really take care of not a single parameter inside this matrix becoming too big, either positively too big or negatively too big. So this is regularization. It allows us to avoid overfitting. There is another method which is more dynamic, called dropout, where we randomly set coefficients of a matrix to 0 during training. This is a way to introduce noise, and so we decrease variance because these zeros will mix up things, but we introduce bias. Besides sigma as activation function, we can use also, there are other functions. One which is quite frequent is rectified linear unit. Rectified linear unit is identity for positive values and 0 otherwise. So it's an horizontal line which at 0 becomes the identity. The problem with this is that it's not differentiable. And there's a big change between 0 and non-zero values. So there are means of playing around with this function. For example, you can change the value where it starts being the identity. You can add a very small slope for negative values. And you can add a maximum value, so it's identity, but until some maximum value. And here is my example. So I, contrarily to naive Bayes and logistic regression, I will not give you the description of every class in Python, and there are far too many of them. I'm using Keras, which is a very nice package for doing deep learning in Python, developed by a Frenchman, François Chollet, who also wrote a very nice book, a book with a lot of code and very nice diagrams, but very few formulas. I'm just giving you the example, the same corpus as with naive Bayes and logistic regression. And let us build a small forward neural network. So why do we call it forward? Because its architecture is going from the input layer to the output layer, and basta. So it's going forward. In the next lectures, we will see recursive neural networks, convolutive neural networks, and so on, always applied to natural language processing. So here in our example, we take the same data, but this time, as neural networks are a bit long in processing, I don't want to use cross-validation. I'm using a manual, simple split, taking 80% of my data for training and 20% as a test corpus. I'm doing this with this Python function that returns the train corpus, the test corpus, train labels, test labels. Again, I vectorize and fit, this time separately for training and testing. And why do we need to instantiate a vectorizer? Because we want to have the same vector for both training and testing. But we build this vector from the training set. So there may be some words in the test set that will disappear because they were not there in the training set, so they are not in the vector. You need to install the Keras package and import this sequential class. Sequential is for forward networks, In the sequential class, you instantiate a model. Here it is empty, and then you add layers. In our case, we have a first layer, which is the input layer with an input dimension equals to what? To the shape of X train. So X train is a matrix where rows are individual, so documents, sentences, if you want, and columns are vectors of my bag of words. Here I'm taking the second dimension. So I need the size of the bag of words vector. It's impossible to know this because it's created when you vectorize. And if you put some randomness, here there is no randomness, but if you put some randomness in the splitting between train and test size, then every time you run this program, you will get a different vector with a different size of words in the training set. So this will be the input dimension, the length of the vector of your bag of words. And this is the output dimension for this layer. So here we are going from X to Z. X has input dimension, the number of words in your bag of words, and 10 as output dimension, which is arbitrary. You could choose something different. And the activation function, in other words, a function that will be used instead of sigma in this probabilistic model of the first layer, here is ReLU. ReLU is a rectified linear unit. And then the next layer, which is the layer going from Z to Y, has as input dimension is not specified because Keras is very kind. It avoids us calculating dimensions of all layers. It will take the output dimension of one layer as the input dimension of the next layer. Here we need to specify it because it's the first layer. And our output dimension will be 1. So we do a binary classification. And activation function will be sigmoid instead of ReLU. Here we have described our neural network. Then we compile it. Compiling means just building the infrastructure. So building the memory slots that will be used for all coefficients, because once you have given the dimensions of every layer, you know how many thetas you have to calculate, how many b's. So by compiling, the system reserves the necessary space in memory, and it builds the infrastructure knowing the loss function. The loss function is cross entropy, and it's binary because we are doing a binary classification. So binary cross entropy is this cross entropy, but not multinomial, binary because we have only two classes, 0 and 1. The optimizer is the kind of stochastic gradient descent we will use. So Adam is a particular method of stochastic gradient descent. And metrics will be accuracy. So what are we measuring in our calculations? Once the model is compiled, we will fit. So fit means training it. To train it, we give it the training corpus, the labels of the training corpus, but also data for validation. So validation is testing done during the training. So we give both individuals and labels. And now there are two crucial parameters, epochs and batch size. What is batch size? Remember we said when dealing with logistic regression, we said that we can calculate on instances of individuals. So here it's something similar. Instead of improving our parameters on every individual, we take averages of individuals. How many averages? As many in the batch size. So this is a way of smoothening calculations. It reduces variance, since instead of relying on a single individual to do a calculation, we rely on more than one, on many individuals. Of course, it depends on the number of individuals you have. It should be ideally a reasonable part of your corpus, and it speeds up calculations a lot. And epochs, it's just how many times we will go forwards and backwards. So forwards, applying our parameters to get a result, then comparing the result with the true values and using this in back propagation to change values of parameters. And then again, forwards and backwards. And finally, the results of this fitting are kept in an object called history. So this model can be used to do predictions, but I can already study its evolution during training. And this history, I can display this history variable. We will see what it means. And I can use the model to do predictions. And these predictions I can do on the training set, which is not a big deal, and on the test set. And ideally, one should have also another test set not used at all while training the model to do further testing. Because here, we're using the test data for validation. Okay, so here is what is displayed on the terminal. First, there is a description of the model. How many parameters? So these parameters are the thetas and the b's. Why are there so many? Because my corpus had many distinct words, and I took them all. We will see that We can also take a subset of words. We can choose the most important words to keep, but here I took them all. And why do we have 11 here? Because we have the 10 output neurons plus the bias. So this is the total number of parameters. So all thetas and b's to be calculated. The training accuracy, 1, of course. And the testing accuracy, it's a bit lower than what we got in the logistic regression, but it's still comparable. It's still around 80%. And of course, this is a very simple network, and we don't expect to have great results with this network, especially since we are using only 10 intermediate neurons. And here you can see the evolution of the network during training. Accuracy on the test set, on the training set, and loss. And remember, loss incorporates also the smoothing regularization factors. As expected, accuracy for the training set, here you have the number of epochs. So during the training, very quickly after 21 times going back and forth, you already are able to predict your training corpus with perfect accuracy. Okay, but on the testing corpus, you are on this level around 80. And it's not really improving. As for the loss, for the training corpus, loss is 0, since your prediction is perfect, but the loss is increasing, meaning that your thetas have tendencies of becoming big, and this means that after 10 epochs, you got the best possible result, something you see also here, and from then on, it's only getting worse in matter of loss. And here's the code to obtain this diagram. So to resume, we have seen these 3 classifiers, and I hope now you see the meaning of this notation, the relation between neural networks and logistic regression, and the tricks we used, for example, the trick of using probabilities as features inside the network, and also representing this loss as a crossed entropy. And this is why Keras calls this loss as, calls it a crossed entropy. We are almost finished. Let me change my screen share. Okay, and here is a lab. On sentiment mining. You will find the corpus on Moodle. It's a rather big corpus. It has 50,000 reviews, and these reviews are sometimes quite longer than the ones we processed during the lecture. So this is a negative one, this is a positive one. It's about movies, so it's more sophisticated than restaurants. The original corpus also has neutral reviews. I have kept only the negative and the positive ones. And I lemmatize the corpus. So you don't need to do it. You can do it if you want, but on Moodle you have all the lemmatized data already. And it's big, it's more than 400 megabytes. Remember CONLL notation for each word or each token. And I added début document, début phrase, fin phrase to structure the data a bit. In this lab, we will use a resource called CentiWattNet. So what is CentiWattNet? It's a resource made by an Italian team, because Italians are specialists of sentiments. And it makes an hypothesis that sentiments can be described in two axes. So let me change the screen share. Voila. So what you see here is the paper. Voila. And they say that we have two axes, but in fact, it's not independent. It's a triangle where you have positive, negative polarity. So a positive feeling and negative feeling, and another axis between objectivity and subjectivity. But why do we have a triangle? Because when we are objective, then there is no positive and negative. Being positive and negative is subjective. Okay, so when I say I like the temperature, it's nice, hot, then this is positive and subjective. When I say that the temperature is exactly 17.5 degrees centigrade, there is no subjectivity at all. So I cannot say that this is positive or negative. It's an objective information. And what CentiWattNet is doing, it's taking a lot of words and placing them in this triangle as being more or less objective or subjective, and when subjective, more or less positive or negative. So that's the idea of CentiWattNet, and I've placed the data also on Moodle. Now the question is, can this help us in predicting positive or negative polarity of movie critics? So I'm asking you to write the Python code that will read the data and the CentiWattNet data and use CentiWattNet to classify the data into positive and negative classes. So you can use a 5-cross validation, use your training set to train your model, and your testing set for testing each time, and you will obtain an accuracy I don't know why I put seconds here. Sorry, this is an error. In fact, for this method, I'm asking for the time your model needed. You can use SVMs or logistic regression, whatever model you like. And here to put the accuracy. Now, in this first step, I'm proposing you to use all words. So take all words, no matter what the postdoc is, and look into CentiWortNet if they are there. And if yes, use them as features of your training documents. And also as features of the test documents, and try to predict a class. Now, if you do this, at least I got a very bad result here. Which means that if I take all words, I have a lot of noise. The second attempt is to take only dependency tree heads. So here, remember in this notation, these are dependencies. This means that this word is governed by number 5, this word, and this is the nature of the dependency, and this one is root of the sentence. So dragged is the root of this sentence. So second attempt, take only roots, 3 heads. Next attempt, take 3 heads and verbs, and then take 3 heads and nouns, and then take 3 heads, nouns, and adjectives. So I don't want to spoil you, but here you will see no difference or little difference, and here it will start, your results will start to improve. And they will improve a lot here. So you will find out that taking adjectives gives you a much better result than taking verbs, 3 heads, or even all words. And of course, you can do other attempts. The second part of this lab is about using neural networks. Here we have a forward network. We can apply it. We can use dropout layers. So dropout layers will remove half of the nodes on each, will set half of the coefficients to 0 on each epoch. And you can experiment with batch size. So batch size is how many individuals I take together. Epochs is how many times I go back and forth. And this is the size of each layer, the number of neurons. And then you can also use other kinds of networks. These are more complex networks, which we will see next time. And next time we will also talk about embeddings, a very important concept in this area. And of course, convolution networks, which are known for processing of images, but here there are 1D convolution networks used for text. So as always, I will put in a few days the solutions with the complete code of every case and the results. I will put them on Moodle so you can check it out. It would be better you try it on your own before that. And this concludes the presentation of the lab and the lecture.